Hi everyone, and welcome to this video on linear restrictions on coefficients inside of a simple classical linear regression model. In particular, we're going to discuss what we refer to as the Walds test of linear restrictions. So if you think about it, there are instances that we sometimes face in multiple regression wherein the coefficients that we have in that regression have to satisfy a specified linear restriction. So for example, if you can think of a Cobb-Douglas production function, so you have here, say, two goods or two factors of production, x1 and x2, with their respective elasticities there. One way for you to be able to linearize this is to put it in linear form. So if you want right now, if we see the regression model in this particular format, right, in this format, it doesn't satisfy the assumptions that we place on a CLRM because the betas that we have here are not raised to 1, right? So how do we make this model or transform this model in such a way that our betas will be linear and raised to 1? Well, we take the natural log of both sides. You take the ln of both sides. So take the ln of both sides and you get ln of y is equal to beta naught, right? Plus beta 1 ln x1 plus beta 2 ln x2 plus u sub I. Essentially, you get this equation that we have here. Now, remember, if it's in a Cobb-Douglas form, the exponents must sum up to 1. So you can actually test different restrictions behind the coefficients that you have. And in this case, we may want to test against hypothesis wherein the sum of the betas in a multiple regression are equal to 1, such that you can prove that the Cobb-Douglas production function satisfies constant returns to scale, given that by assumption, the exponent should sum up to 1. Now, let's try a simpler example, which is, for example, we have this particular regression model here below. And let's try to impose the restriction that beta 2 is equal to 0. So if we think about it, if we have this model, so we have here on the dependent side, which is the college GPA. So this is the GPA of a student in college. And we're trying to regress this against the high school GPA and the amount of alcohol consumed. Now, obviously, it might mean, well, based on maybe logic or how you would put it, people or college students who go out to drink more often generally have lower time or less time to study. Hence, we would think that the college GPA wouldn't be as high as compared to someone who doesn't drink a lot of alcohol. And that's by assumption. Now, what we'll see is, let's try and impose the restriction that beta 2 is equal to 0. And if beta 2 is equal to 0, right, if we assume that this is equal to 0, it's as if this component doesn't exist at all. It means that there is no relationship between the college GPA and the alcohol consumption. So essentially, in this formulation, we're saying that we believe, at least we're going to impose a linear restriction that alcohol is not a significant determinant of the college GPA, right? So let's try to formulate how that goes in a Walds test. Well, effectively, we try and form two models, right? So we have our model, our first model, which we refer to as the restricted model. And this is the model wherein you put the restrictions in place, right? So our assumption earlier was that beta 2 should be equal to 0. So you have here in your restricted model that there is no beta 2, right? No beta 2, or beta 2 is equal to 0. So this is the model that has the restrictions. And you're going to try and compare that with an unrestricted model, which is a model with the restrictions not in place, right? And the unrestricted model is just our original model, which we have there. Notice that beta 2 is allowed there, right? And it's assumed to be some value, whether positive or negative, right? But it's not, should not be equal to 0. So if the error term, under the assumption, the normal assumption is that the error term is assumed to be independently and identically distributed, well, we can use the generalized form of the test statistic that will test for the validity of the linear restrictions in the model below. And the F statistic that we're going to compute for is essentially we're gonna regress, we're gonna run this we're gonna run each of these models, the restricted model and the unrestricted model. Then we're gonna use their RSS and their degrees of freedom, right? So we're gonna calculate for all of that. And if we plug it in this formula, we should get an F stat. Then we compare it to this critical F statistic and we should get a result. Okay, so effectively, right, when you run a regression, you will derive the RSS. Effectively, it will show the results of the RSS, and it will also show you the degrees of freedom associated with that RSS. And once you plug in everything to the formula, you get an F stat. Note that this M here, this is essentially the number of restrictions, right? This is the number of restrictions in place. So if you recall, in this particular model, we just have a mere one restriction set in place, which is that beta 2 is equal to 0. So that number is 1. Alternatively, M is also equal to the degrees of freedom of the restricted model minus the degrees of freedom of the unrestricted model. So you could compute for that in two ways. Just know the number of restrictions, or you can just subtract the 2 degrees of freedom. So the null hypothesis is that the restriction is valid. What this means is that if we find that the restriction is valid, it means that our beta 2 is equal to 0. However, if when we do the testing and we find that the restrictions are not valid, then it just means that beta 2 is not equal to 0. Note that we are going to do a sort of two-tailed approach in this case, in that it not being equal to 0 can imply that beta 2 is greater than 0, or it could be beta 2 is less than 0. So for this case, we do a two-tailed sort of case, just a more general case, and use the not equal to. But you can just have it in one of these one-tailed directions. Okay, so for example, this is the results that we get from the restricted model. And what we do, okay, so you see here, this is the sum of squares of the residual. So essentially, we use that value, that's 16.07, and this is your RSSR, right? That's the residual sum of squares of your restricted model. Note that this is the results of the restricted regression that you have there. Then after that, okay, you run the model now with no restriction. So this is your unrestricted, and you can see that it's unrestricted because we have an alcohol there. And what you do is this value here is now your RSSUR, right? That's RSSUR. And here you have here your degrees of freedom of the, whoops, sorry, not that one. Okay, so you have various things here. And what you do is you can plug it into our formula. So this will come quite simply. Okay, so you have here this particular case, right? So let's sort of see how this is computed for. Well, you have here, okay, this RSSR is the number here. That's this one, 16.07. This 16.04 is this number here. That's this one, 16.04. Now, how did we get 141 minus 2? Well, 141 minus 2, so if you consider everything that was estimated, okay, so this corresponds to the degrees of freedom of the restricted model. And then this is the degrees of freedom of the unrestricted model, right? So you have, in your unrestricted model, you had 3 parameters to estimate, that being beta naught, beta 1, and beta 2. In your restricted model, you just had 2. That was beta naught and beta 1, right? Because we set beta 2 equal to 0. So 141 is the total number of observations you have in each, okay? And that's that, right? Then you just copy again the RSSUR, right? And then this is the same as your DFUR. And if you get something, you'll get some value of your F statistic, right? So what you do is, this is your critical F, right? This is your actual F rather. What you do is you compute for a critical F statistic by just using some statistic table, and you can find that this F statistic with this specification is equal to this test statistic. So that's 3.9 versus 0.189. So since the computed F statistic is less than the critical F statistic, we failed to reject the null hypothesis. Hence, our opinion was validated. we don't necessarily see some relationship between alcohol and college GPA. It's quite a too far off relationship. Maybe if it was something like a test score or the hours of sleep, that would be a better determinant, but not really alcohol consumption. Hence, we say that the restriction we imposed is a valid one, right? It's a valid restriction. Therefore, the number of times the student drinks does not affect the college grade point average. So that's a brief introduction of the Walds test and how it works and how you can compute for the test statistic. And thank you very much for staying along in this video. I'll see you in the next video. Thank you very much.